Hi, thank you for such a great kind of keynote talk talking about the challenges of artificial intelligence and how it's going to be playing a role in engineering going forward. I think I agree with a lot of the comments that were made. I don't think AI is particularly a panacea that can be used just to solve all engineering problems, but I think it's undeniable that we're in an era of AI, and it's important to understand what AI is as a tool and how, I think any engineer that's going to come out of school now better understand what AI can do and when and where to deploy it. I think anytime you come to a complex system, it is going to be a critical thought process and not just something unique to the computer scientists to deal with. And so I'm excited to talk about a piece of technology today that we've been working on, trying to incorporate AI to solve some serious engineering problems. Right now, we're focused, what I'm going to talk about now is more, I guess, for a wired connection, not less wireless communications, but I'm excited to have some conversations afterwards about how this idea can be applied to some of the problems you're solving with. Okay, so just to start with, I want to talk about the kind of the problem space that we're looking at. I think everybody here has heard the news about this radical investment that big tech is making into data centers, right? The picture on the left here is of the Hyperion data center that Facebook is planning to build that is the size of Manhattan. Right? The expectation is that they're going to spend $1.4 trillion to build out the data capacity for the AI infrastructure. And the point of these systems is to do these incredible AI calculations and all the process there. And the problem is that a lot of the workload that is done on these data centers is really bottlenecked by networking, right? You're doing calculations and sending it across a network, and the speed of transmitting that data is actually the real pain point that is suffering for that. Right now, for high-speed data centers, you have connections there that are about 100 gigabit. That's single-lane connections, with 200 gigabit coming online now. But the expectation is that by the time that this data center is actually built, the industry is expecting that data rate is going to keep doubling, and that by the time that Hyperion is actually constructed, we'll be at 400 gigabit lane rates, right? So that's a radical continual improvement in data speeds. The challenge is that this is really hitting a fundamental problem in physics, where if we follow the same approach as normal, if we want to increase our data rate, we're just going to double our signal speed. The signal speed required to hit 400 gigabit is beyond the carrying capacity of copper interconnects. You just cannot send that data across that wire. And it's a problem that the industry just hasn't faced before, and there's a big challenge as to how to get around this issue. Realistically, the industry sees kind of three options to deal with this issue. One is to try to improve the copper interconnect, so maybe try to push this cutoff frequency out a little further so you can squeak out some more data. Another option is maybe to switch to some more interesting substrates like silicon photonics or change some of the approaches there. But the realistic solution, sorry, the clickers, is that working? Okay. The most likely solution here is to change the encoding schemes. So right now for high-speed communication, the way this works is you send signals using a PAM4 encoding, right? So you're sending it as 4 voltage levels, not just as a binary signal. And the likely option is if we have a fixed bandwidth, and this is all we can really play with, the idea is we have to move to a denser encoding scheme, something like PAM8, where you're sending more data per a symbol there. The challenge is that 10, 15 years ago, the industry, as it transitioned from NRZ, from binary data to PAM4, they didn't make that transition lightly, right? They extensively studied the higher encoding schemes and trying to move to those denser approaches. And what they found is that if you actually try to move to these encoding schemes, signal integrity becomes a major problem, right? To build out these approaches, you can see here on these eye diagrams that we have these nice clear eyes at PAM4, but as you go to denser encoding schemes, they get much smaller. All of a sudden, thermal noise and timing jitter become incredible problems. And you end up losing the ability, like while you can pack more data per symbol, you're actually, because of the mistakes you're making, your data rate is slower and these systems fail. So it's really, this is the most likely solution for the industry, but given the traditional techniques and the traditional solutions, the current approaches can't really take advantage of this approach. So we need to kind of think outside and come up with some new solutions to this big problem, because there's a huge amount of pressure. And if the industry can solve this 400 gigabit problem, an incredible market return is expected out of that. So what's our innovation, right? So the idea here is we're trying to step back and rethink analog to digital conversion from a machine learning perspective. The idea here is, and just as a simple diagram of the workflow of our device, the idea is you have an analog signal, It comes into our system, that's our analog front end here, which breaks up that signal into a collection of features. The idea is that each one of these green boxes is capturing some bit of information about that incoming signal. And so the idea is the signal comes in, it gets broken up into a collection of features, and then we can pass that data off to a neural network, and that neural network can then synthesize the digital signal on the other side. So again, the idea is just that it comes in, breaks up into parts, and then the neural network reassembles it. And the purpose of framing it in this approach is we're trying to design that analog front end to take advantage of really the power of AI. The idea is that this neural network can do very complex, very nonlinear, incredible calculations. And the idea is that if we can, this allows us to build an analog front end that can represent the information in the signal in some complicated, nuanced format that you and I as engineers may not fully understand, but we can kind of say, okay, we've captured all the information here. It's embedded in some confusing state. And it's the job of the neural network to figure out what all that data means, right? And we can do this in this way of separating, capturing the information of that analog signal from interpreting that data. Because traditionally, if you want to be doing analog to digital conversion, you have to build a pristine mixed signal circuit where you have all of the analog components and digital components working together to perform those standard Shannon-Nyquist approaches. But again, just to reiterate, our thought here is trying to reframe analog to digital conversion as a signal comes in, gets broken up into parts, reassembled, and you get the same data stream, the same digital sequences out the other side. It's just a black box. You don't have to, none the wiser if you're just dealing with this data downstream. Now, so far I've spoken very abstractly. I've just said green boxes and features. What do I mean by that? I think there's a lot of things and a lot of ways we could do that, and there's some creative ideas of what we could put in these boxes, and I'm excited to talk to some people to find out what you could think about it. But as Baby's first attempt here, we decided to keep it as simple as possible. The concept is in our analog front end here, what we're doing is we're just going to deploy a bank of bandpass filters. The idea is we have some spectrum of interest for our signal, and what we can do is we can slice this up into a set of different windows such that each one of these boxes represents a frequency domain of that signal. And as long as we kind of tile the entire frequency space of that signal, I think we all can agree that the information of this signal is captured in the output of our analog front end. Now, I'm not the first person to think about, oh, we could capture a signal using bandpass filtering and doing this frequency reconstruction. But the interesting part here is what we're going to try to do because of our neural network approach here is we're going to build these circuits, these bandpass filters, out of very, very simple elements. We're just going to use a first order high pass, first order low pass. And that's going to result in a filter design here with broad roll-off, complicated aliasing when you downsample this signal. It's going to be a messy, messy problem. And the idea is that the output of this system is going to be complicated because when I capture this frequency band, I'm going to get a little bit of information here, a little bit of information there, and it's just going to be a mess. And it's going to be a problem that you and I as engineers really would not want to sit down and solve. It's just a nightmare there. But the nice thing is we don't have to. That's the point of this architecture here. So again, the idea is we want to keep this analog front end very simple, using very, very simple components, but still capturing that information. And I know that there's a lot of AI skeptics in the room, and I appreciate that. The intention is we're trying to obey Shannon-Nyquist here, right? We think information is contained in this data. We're not making stuff up. We're just trying to capture it in some different format. So we're trying to preserve all of that rules there. So the idea is, okay, so we can design our analog front end, match these filters to the signal of interest, and then what do we do about the neural network? So the idea is what we can do is after we've finalized our circuit here, we can then train our neural network to perform this task. So the idea is we take a neural network out of the box, it doesn't know anything, it's just completely random. And the concept is because either through simulation or through test devices, what we can do is we can feed into the front of our system a set of training signals. And these are just random wideband signals based on what you're actually going to be seeing as you deploy this device. And so the idea is that signal propagates into our device, we split up based on those features that we have, and then we can pass it off to the neural network and tell the neural network, hey, we measured this, we fed this into it, get us back to it, right? And so then using the magic of neural networks, the system can then, using just standard, this is basic machine learning here, with we can effectively generate infinite amounts of training data because we can just feed in data into the system here. we can then just have the neural network do the wonderful tasks of adding, subtracting, do all the complicated nonlinear functions that neural networks are intrinsically trained to do. And from like a high-level perspective, the concept here is really that neural networks have been known since the 80s to really be function approximators, right? That's one of the core things that they're used as. And in this context, you could kind of think of what this neural network is doing is it's learning the inverse transfer function of our analog front end, right? And so the idea is we can simulate this by pumping in data into it and recording what comes out the other side. And the advantage of that is that this is just a fully automated system. It doesn't know anything about what these are. It doesn't know anything about a bandpass filter. It doesn't know any of the context or the cutoff frequencies. It is just simply saying, you fed in billions of examples into the system, you recorded that data coming out of it, and now I can adjust that data here. And to be clear, this animation you're seeing here is actual data of the neural network training to learn to do this task in a system like this. But so again, the idea is in our system, we define our analog front end, we run this training, and this all is done a priori. So this is just, at the end of the day, once it hits a metric that we care about, we can freeze the training and say, okay, the resulting neural network has learned the behavior, the properties of this analog front end, and we can fix that and then just treat it as an operating in inference mode from there on out. Now, the other thing I want to reiterate here, I know that there's a lot of, the previous excitement in AI or in analog to digital conversion was compressed sensing and this idea that maybe the signals that are coming into it have some structure, and if we exploit that structure, we can take advantage of that. What I'm describing here, the idea is that we have no knowledge, we're not learning anything about the incoming signal, right? We're feeding in purely wideband signals, and we're not exploiting the fact that there's some pattern in that structure. The idea is we're really trying to just learn the physics, the device physics of those analog components. And so again, the idea is after we trained it, hit the performance metrics, the bit error rate, the signal to noise ratio, whatever the metrics that you care about, we can freeze the training and then just stop it and say, okay, here's the device that we have. A signal now comes in, it gets broken up into a collection of features. This neural network has already learned how to do this task, and it spits out the digital signals on the other side. And that can be done very efficiently, where all of the neural network training and all of that slow, expensive process is done a priori before the device is even deployed. Okay, so what I've described so far is just a very generic analog to digital conversion. What is the application of this, and why are we excited about this as a potential solution to the problem I originally stated? Well, one of the exciting approaches or advantages of taking this machine learning approach is we can do some things that are a little outside of the box and not traditional in how you would think about applying a standard analog to digital converter. So this text got a little weird, but so we want to apply this initially as our initial target here for a SerDes application. So again, the idea is we're sending data across a wire here at 4 different voltage levels. And the idea is in a traditional SerDes receiver, for this system to work, you have to have your receiver fire and sample exactly in the middle of those symbol windows, and to keep in lockstep as that system goes across such that you can read your data downstream on that system. And a considerable amount of engineering and time and effort goes into keeping this clock nice and in line with that approach. So our goal with our system, and this came through just analyzing how our device works, what we're showing here is that we want to be able to slow down our clock rate so we can start sampling our system at a sub-data rate limit here. The next option that we want to do is we want to be able to allow clock drift such that our receiver no longer has to be coupled tightly with the transmitter. And then the third big one that we were interested in is dealing with clock jitter. So the idea is we know that there's no such thing as a perfect digital source. Every single strike of a clock is going to have some random variation such that this strike could be a little late, this could be a little early, and you don't know, right? And so the goal with our system is that we want to take our neural network and this neural network machine learning approach to analog to digital converter and be able to run in a PAM4 signal that looks like this, sampled with a timing approach that is slower, allows clock drift and jitter in the approach, and still recover the same data rate on the other side. That's the big task. That's the big thing that we're trying to throw our approach at. The reason we think this is important is I think it simplifies, not only because I think it's going to address the industry problem I mentioned before, but it actually it can simplify the implementation design of these traditional SerDes receivers. So in a traditional SerDes, you've got a channel where the signal's coming in, some equalizers, a bank of ADCs. You then do some digital post-processing, and that's fed back into a clock data recovery loop. And the idea is that you have to be very accurate, and this whole loop is what defines the timing and all the alignment of those approaches. And if our system is able to achieve what I just laid out there, I think we can eliminate that feedback loop. We no longer need to use the output of our system to change the timing of the system. And as a result of eliminating that, it actually reduces a lot of the complexity of the implementation of that device, the power performance of it. We think we can get a lot of advantages if we're able to do that task that I've just said there, of the slower data rate, drift, and jitter. All right, I hope everybody's with me here. So we ran some simulations, and then we were awarded an NSF SBIR last year, and we actually just finished the results as of the new year. So the stuff I'm going to show you here is just days old. But in general, we built like a mock SerDes link. So this is at the Caltech Innovation Center. The idea is we have a transmitter here that serves as our PAM4 generator. And in this picture here, you can see it. Here, this is just off-the-shelf components that we purchase as high-speed DACs and high-speed ADCs. So the idea is this is an FPGA connected to our DAC that's acting as our PAM4 transmitter. It sets a signal over this black cable as our connection, our channel there. That then gets fed into our bandpass array that splits it up, as I mentioned, those kind of frequency bins there. And then the results get digitized using a bank of ADCs on the other side. And the idea is with this platform here, we're able to then play around with the timing to get those exact effects that I was trying to show you. So just to show some results and the signals that we're getting out of this approach, the top plot here this is coming from the simulations we ran. This is just from our SPICE simulations. What you can see is this is an example of a PAM4 signal that's being sent into our system. And these green lines represent every strike that we take a measurement from our array. And the things that I'd like to highlight is just that we have a symbol here, the signal transitions, it transitions again, and then we fire. And then we wait multiple signals again. And the other thing I would like to highlight is that the timing between these two strikes and these two strikes is different, considerably different there, and maybe a little hard to see on this screen. But in general, in these simulations, what we tried to do is we model our system at running at 1/3 the data rate of our system of a traditional receiver. We allowed a 0.1% clock drift, so that's every 1,000 symbols sent over the wire. We just phase in and out of the clock there. And then the thing that we were really interested in is we chose a 10% jitter of the whole clock cycle. So it's a massive, massive amount of jitter, just showing that we're really invariant to when exactly each one of these clock strikes occur. Now, the plot over here on the right is of results that we recorded from our PCB demo that I just showed you there. And this is kind of an eye diagram. The challenge is because we're at sub-data rate and we're doing some weird processing of the signal, it's not exactly a one-to-one eye diagram. But the idea, at least I want to show here, is that the data that we have is extremely, extremely messy. If you were to look at this collection of traces here, I don't think anybody would really be able to tell you what signal level we're sending or what that data is. It's not intuitive as to how we've captured that information. And so again, just showing you the results of this approach there. So the nice thing is we were able to show that both in our simulation, so we did a simulation both in SciPy, just as a version of MATLAB Simulink, and then built that into an LT Spice. This was before our NSF project here. The idea is that initially you start a neural network. It doesn't know anything about the system that you've built. But over a very short period of time, the performance of the system drops down and hits the threshold that the industry requires for this is the raw bit error rate before error correction in our system. So it's able, given exactly the timing structures that I showed here, so exactly the data that we captured from this kind of plot here, our device, the neural network performance, was able to hit the industry standard raw bit error rate, which then gets deployed. So then we repeated this experiment with our physical device, as I mentioned, feeding into PAM4 signals. And what we found is that prefect, so this is before any of the error correction, we were able to hit about 10 to the -5 bit error rate. After we proved out that we were hitting kind of the industry threshold there, what we did is we then applied some standard Reed-Solomon encoding and fed over error-corrected signals and found that the performance of our system radically improved. The idea, I put here 10 to the -10, the challenge was we were only able to record in the given amount of time 10 billion examples across the wire, and we found no errors. So the reality is that our system can perform much better. maybe I've gotten a little confused here, but the point is that in the traditional approach, you can take a raw bit error rate of something like this and crush it down to what the industry cares about. And from our results, because we've introduced this neural network, the types of errors that we get are very similar to what the industry is already expecting. And as a result, the standard kind of error correction techniques can be applied to the output of our device, and that it's an easy kind of drop in there. You don't have to rethink how we're transmitting data or the errors as a result of that. Now, the results that came just this week is we upgraded the signal, the encoding of our signal to a PAM8 signal. As I mentioned, I think the industry is going to have to transition to a denser encoding scheme to that approach. We just changed the transmitter in our approach, send in a PAM4 signal, and we're able to train a neural network that had similar-ish performance. There was a mild degradation in the bit error rate, as to be expected, because there's going to be more noise on the signal. But the reality is it had remarkably similar performance, and this is with a radical amount of timing distortions in these approaches. We haven't had time to do the post-error correction on it, but I think it's going to look very naturally to the same thing that we had before. So again, I think it's been exciting that given the radical kind of task that we set for ourselves of sub-data rate with drift and jitter, we were able to show that this neural network can perform with the industry's kind of standards as they expect. So the last two comments just that typically kind of we get asked in these conversations here is how do you deal with latency, right? So typically when you're doing processing of these signals, you need everything to be very, very fast. One of the things that we're excited about is we think we can actually take advantage of error correction in our system to exploit for power and latency savings. So the idea is that traditionally, as you're sending data across a wire, you're not just interested symbol by symbol by symbol, you're actually sending it as a full code word, right? So you have some message you want to send, you've packed on some parity bits, and in traditional kind of SerDes applications, you'll even interleave multiple code words together to kind of alleviate or handle burst errors or all kinds of challenges there. And the reason that's important is that by the time you start sending data, you have to naturally, based on the natural kind of process of a SerDes device, you start sending data, you have to wait until you get the end of it in order to decode and do all the error correction. So it doesn't really matter if you can accurately predict what this symbol is immediately. It only really matters once you get to the end of this process there. And so as a result, if we can wait that period of time and decode this just code word by code word, right? So the idea is if we process the code rate, not the symbol rate, we can get some radical performances gains, we think, on the power consumption and some of the abilities there. So that's just kind of one of the things to deal with that. The next point is we think one of the exciting applications here is that we know that the channels that are being sent across here are not static. There's a lot of dynamic things that happen. So the environment can change, all sorts of age and all these kinds of things can alter the performance of an individual channel. And what we can think in our system, one of the nice things that we think we can very naturally incorporate that information, if we can capture or measure the health of that link, it very naturally fits into our system, where if we have some monitor that's capturing the environment or the current health of that system, that's just a new input to our neural network, right? The neural network doesn't know, as it starts, that this is all bandpass information. It'll just naturally incorporate this data into its performance and can respond to it. So the idea is we don't have to change or update our model on the fly in response to the environment. We can just actively take this as information, and that goes fed into the calculation that the neural network automatically learns how to do. So that's just a way that we can exploit and take advantage of the neural network as being this really broad, open platform where, again, the neural network has no expectation when it starts training of what you're feeding into it. So why don't we just feed in more information to it? So with that, I'll summarize. So the kind of the process that we've been going so far is we started off with some simulations here, as I mentioned. That's led to our NSF SBIR, where we built out our physical prototype with using some just off-the-shelf components to show that this isn't just a fluke of the simulation. And now we're moving on into building out an integrated circuit to really demonstrate this effect as a product. Our goal is just to build out that analog front end as the initial demo, and then move that out to a complete circuit with the machine learning on the end there. And so maybe I've gone a little quick, or I apologize, but with that, I'm happy to take questions.
Hi, I'm not a RF person. I'm a AI ML person. So I was wondering, How do you model the jitter? Like, is it something that you can model with a RNN? How do you model that dynamics?
Yeah, so that is physically built into how we actually have the device there. So that's in this idea. So in the physical system here, we're able to manipulate the clock that is timing the circuits, right? So that's not being modeled synthetically in the neural network there. So that's like a physical process that we're applying to the system.
But how do you model the real jitter? Like, can it be modeled as an RNN?
Right now, our the neural networks that we're deploying in this, you could use an RNN. We're using very, very simple neural network implementations here. So there's nothing really, we could talk more about the details of how that gets implemented, but right now we're not involving like an RNN in this approach. But again, the way that so you're asking how do we model it internally in the network, not in the simulation?
To be successful, to compensate for that dynamics, right? You want to fit the right architecture to that model.
Yes.
To that dynamics, right?
Absolutely.
That's where I'm coming from.
Yeah, entirely. I think what we've discovered is because we have so well defined what this problem, this neural network is trying to do, right? The idea is that because this is just trying to do this task of going from here to there, we have found an extremely simple neural network is able to do this task, that we don't have to get so fancy with the design architecture of our neural network, and that the information that we're capturing from our analog front end contains all the relevant information. And so using those more interesting RNN approaches isn't particularly necessary there, but I'd love to talk more about it offline to understand how we could kind of take advantage of it.
I have a question. So how many ADCs did you use and what was the sampling rate?
Excuse me that again?
How many ADCs did you use for your, what is the bank? I see at least 8 in your figure.
So yeah, so in this approach, so this is the initial design here. We have just a small number of filters. Maybe that's a exact number that we'll talk about maybe at a different time. And this system here, just based off of the constraints of the off-the-shelf components, is in the low gigahertz range of this data.
So do you even need, I think my guess is following, right? If you were to do this, I could just put a bunch of bandpass filter and direct ADCs, and I can reconstruct the data without even the ML model is my sense, right? Because each bandpass filter will create a different delay, group delay, and I can just essentially take, even if your clock is poor, I can decode this without any ML, right? Real standard techniques.
So I would say with standard techniques, if you're trying to do strike-to-strike variations with this approach, you're losing information with the standard system there. And I'm not sure you'd be able to do it.
If you put a bandpass filter with different group delays, each of them will automatically get shifted when you sample them.
Absolutely. Yeah, of course, there's going to be some phase delay. And in our system, we incorporate that phase delay by changing how the clocking timing gets to each of our systems. But I think if the timing distortion is completely random from strike to strike and the phasing of it doesn't really, then all of a sudden incorporating that data is not an intuitive thing. I'm not saying the information isn't there, of course, because the information
No, it is there.
here.
I think I'm not arguing that. Yeah.
Sure.
I think, this is like...
Oh, yeah, sorry if I'm taking...
No worries. It's okay. I think there are a lot of questions on this, but
Yeah, great.
One more short question, because I can see...
yes.
Yeah.
So Luke, very interesting. Look, I mean, I've got tons of questions on
Great.
this, but I'll just pick on one. So it seems to me that you're not really using a clock as a clock data recovery system. You're asking your neural net to both do the decode and the clock recovery in one step in some fashion. I'd love to hear some comments about what the training time is.
Yep.
Have you considered, we know what the patterns are for worst case eye diagram issues
Yep.
in a traditional receiver. How well does this perform relative to that? To the earlier discussion about AI, I see these lovely things and okay, it works, but the reality is, okay, take this method, compare it with the existing method for the same power consumption or, how does the power compare? What's the real performance? Does it improve the accuracy? Or is it just, another fun way of doing it?
Yeah, so I would say in particular, so we're moving from our PCB demo to an integrated circuit to get better at those questions of exactly what are the power savings and the specific challenges that we have there.
You could build a standard receiver out of the same components you've got here.
Yeah, but the problem is that the ADC banks here are slower. We'd have to get a different receiver on the other end because, as I mentioned, we have like a sub data rate of our system here. I would say so. There are interesting questions exactly to that point there. I think the reality is that given the kind of the timing ability, or this jitter tolerance that we get immediately from our system, again, as you said, we're training it in one loop to synthesize that data and deal with back calculate those parameters. I think a standard system trying to implement a digital calibration on that, it wouldn't be efficient or obvious to me how that system would work. And I apologize if I've forgotten the last half of your question.
No, that's okay. And then just one kind of observation is you started this presentation with kind of the power versus frequency challenge and the loss through cables.
Yep.
I don't know that that's solving this problem. It may solve your CDR problem that we have and several other things, but ultimately if there's not enough power to detect the signal, I don't see how this solves that issue, which is just we're fundamentally out of bandwidth in a copper cable.
I think that the intention here is to suggest that because of the resilience to some of these signal integrity issues, you can pack more data into the fixed bandwidth that we already have, and that if you can put more power into that range, then you could get it on the other side. The issue is that you literally can't send data fast enough as it is. But I'd love to talk about it offline.